Alright, I want to do another video with a little more practice on cross sections. So an area bounded above by the function sine x, below by the x-axis, on the interval from 0 to pi, is the base of a solid with square cross sections perpendicular to the x-axis. So let me do my best to draw that. So we've got these squares coming up kind of off the page, or off your screen, I guess, like that. And I always start by just drawing that shape. Okay, here's a square. The area of a square is base squared. But we're actually talking about this in 3 dimensions, so the volume is base squared dx. Okay, where that dx represents the thickness. So I go to integrate from 0 to pi, and the base is just the value of the function. So sine is equal to the base. So I end up integrating sine of x squared dx. And you could do that with a double angle identity. You could use your calculator to do that. But I'm going to rely on the fact you could integrate that either with technology or with some trig identities. Alright, an area bounded above by the function sine x and below by the x-axis on the interval from 0 to pi is the base of a solid with semicircle cross sections. So now I've got semicircles. Okay, something like this. Okay, so again, I would start by just, I've got a semicircle. Area of a semicircle is 1/2 pi r squared. Okay? But we're talking about a 3-dimensional shape here, so the volume is 1/2 pi r squared dx. So we go to integrate this. When we do it up here by the problem, we're going to have the 1/2 pi out front because it's a constant multiplier. Integrated from 0 to pi. Now, what's tricky here is that the function sine does not represent the radius. The function represents the diameter. Okay, so we need to take our function and divide it by 2, then square it. Okay. Now, again, I know I mentioned this in another video, but a lot of times people will look and say, well, why would I have to divide by 2 twice? They do different things. The 1/2 out front of the integral, that's because we're only finding the area of half of a circle. Dividing the function by 2 is because the function represents the diameter, not the radius. So we really do need to do both things. Now, if you wanted to do this integral by hand, you could square it individually, square sine and square 2, and then maybe pull the 4, 2 squared out front, and then you'd need some kind of trig identity to finish off. Okay, let's finish this part up. An area bounded above by the function sine x, below by the axis, with rectangular cross sections perpendicular to the x-axis, whose height is twice the base. So now we're building up like this. Okay, so we've got a rectangle where this is b and this is 2b. So the area is 2b squared. So thinking about it in 3 dimensions, then the volume is 2b squared dx, where dx represents that little width. And again, the base is just, in our case, sine. So we'll integrate. I'll bring the 2 out front. We'll go 0 to pi of sine x squared dx. All right. Find the volume using the area between the y-axis and y equals x cubed on the interval from 0 to 2 as base, where each cross-section perpendicular to the y-axis is a semicircle. So now we're talking about building like this. Okay, so, we know the area of a semicircle. Okay, now volume, a little bit different here. You notice that the cross section's perpendicular to the y-axis. What that means is that my little thickness, when I start drawing that in, my little thickness is a dy. So as I go to do my volume, I'm going to have 1/2 pi r squared dy. Okay, so it's just a subtle little change here, that when it's perpendicular to the x-axis, dx is the thickness of our little prisms. When it's perpendicular to the y-axis, dy is the thickness of our little prisms. So we need to make sure and be careful of that. And as I set up this integral, 1/2 pi up front, and integrate, and it is going to be dy. So that means I need to go up here and rewrite the equation as x equals the cube root of y. And remember, it's semicircles, so this is the diameter. So my radius will be divided by 2. And my bounds, well, it starts at 0 and goes to 4. Like that. Our last problem. If f of x is x squared and g of x is x, the two functions form the base of a solid that has rectangular cross sections perpendicular to the x-axis and has a height twice its width. So essentially we're perpendicular to the x-axis, and it's coming up off your screen like that. If I can draw that at all convincingly. Okay. So we've got a rectangle, and the base is b, so the height is 2b. I wish I'd made it different than the other one we did. So the area is 2b squared, so volume 2b squared dx. And again, it's because the thickness is relative to the x-axis, okay? Where in the previous one it was relative to the y-axis. Now, we go to integrate. These two functions intersect at 0 and 1, so we got to get the base squared, and the base is simply the difference between the top function and bottom function, like that. And again, be very careful. The biggest mistake with these is the mix-up between revolution and having to do the area of a circle minus the area of a circle and being able to just find the difference between the two functions. The reason here we can just find the difference between the two functions is that difference represents the length of the base.